Welcome to Dreaming Scientist's Sleepy Stories, a place where the mysteries of the universe guide you toward peaceful sleep. You allow yourself to breathe a little slower, and in that quiet space, a simple truth drifts into your awareness. Even an electron can melt back into light. When an electron meets its mirror twin, the positron, both dissolve without a trace, leaving behind only two gentle pulses of gamma light, each carrying 0.511 MeV. It is as if matter were nothing more than light folded into a tighter, more intricate shape. Tonight, you move softly into one daring question. Approach not with urgency, but with calm curiosity. The idea proposed by Williamson and Vandermark, that an electron might be a single photon curled into a toroidal loop, a ring of trapped light whose natural twists give rise to the charge, spin, and magnetic moment we measure. As your thoughts settle like dust in still air, you drift toward the first piece of this puzzle. Why would anyone even ask whether an electron is made of light? There is a moment in physics that feels like a whisper from another world. When an electron touches a positron, both vanish cleanly, leaving only radiation. No fragments, no residui, no hidden particles, just light. A transformation so elegant that for more than a century, it has encouraged physicists to look at matter with a softer, more uncertain gaze. If matter can turn into light so perfectly, perhaps matter and light are more alike than we imagine. The idea is bold, but not new. In the early 1930s, experiments at Cambridge revealed the reverse. A photon brushing past a nucleus could split into an electron-positron pair. Pair creation. A symmetry written into the fabric of existence. Light becomes matter, and matter becomes light, each transformation honoring the balance of mass and energy. Decades later, NASA captured the essence in a single, quiet sentence. When energy is concentrated enough, even the vacuum can birth particles. And so a question formed gently, persistently. If light can create electrons, could electrons themselves be stable shapes of light? Not metaphor, not poetry, but literal geometry. A structure of electromagnetic fields curled into a precise configuration that behaves exactly like the electron we know. For decades, this question lingered at the edge of mainstream thought. Too unconventional, too different from the electron, as a dimensionless point. But in 1997, John Williamson and Martin Vandermark decided to explore the idea as engineers, not dreamers. If the electron were made from a single captured photon, what shape would reproduce its exact properties? Their answer, a torus, a closed circular path where a circularly polarized wave folds back upon itself. One wavelength wrapped into a stable orbit, a photon coiling around a ring in such a way that its own electric and magnetic fields cross and sustain each other. To many, the idea sounded eccentric, but it had roots reaching back through physics. Maxwell showed that electromagnetic waves carry momentum. Arthur Compton demonstrated that photons behave like particles when they collide with electrons, shifting their wavelengths in precise harmony with energy transfer. That special scale, the Compton wavelength, is exactly where Williamson and Vandermark built their loop of light. Within that loop, fields twist in two dimensions at once, around the torus and along it. This dual motion creates the strange 4-pi behavior of spin-1/2 particles, where a full rotation returns the system to its original state only after being doubled. Hard to picture, simple to express mathematically. The toroidal model gives shape to this rule instead of treating it as a built-in mystery. And then comes charge. If the electron were truly a dimensionless point, its electric field would hold infinite energy. Scientists knew this more than a century ago, long before quantum theory. To manage the infinities, physicists relied on renormalization, a calculation technique that adjusts equations without answering what the electron actually is. The photon torus model attempts a physical explanation. Charge arises from the asymmetry of a circulating electromagnetic field, a natural imbalance created when the wave bends around itself. What makes this strangely compelling is that the universe already forms similar structures. In plasma, fields twist into knots and rings. In nonlinear optics, light can trap itself into self-sustaining packets called solitons. Even the vacuum is not empty. Schwinger showed that an electric field above 1.3 times 10 volts per meter tears pairs of electrons and positrons out of the void, a sign that space conflicts, hold tension, and perhaps confine intense electromagnetic waves into closed loops. Other hints appear across history. Louis de Broglie suggested that every particle carries an internal frequency. The Lamb shift revealed that the vacuum's fluctuations subtly alter the electron's energy. Magnetic resonance studies in the 1960s showed tiny variations in the electron's internal response to fields. Each discovery opened a small gap, a gentle question: is the electron more than a mathematical point? Williamson and Vandermark did not claim proof. They offered a candidate, one that satisfies relativity, Marche's measurements, and avoids infinities. A model that does not contradict annihilation, the Compton scale, or the rules of spin 1/2. It simply proposes a structure that could behave exactly like the electron we observe. Many physicists remain cautious. The standard model still treats the electron as point-like, but doubt does not erase the puzzle. Annihilation remains. The perfect transformation of matter into light continues to whisper. As Carl Sagan once wrote, science can open doors to a quiet kind of spirituality, the wonder that arises when a simple observation reveals deeper structure. If electrons can become photons without leaving anything behind, then we cannot help but ask, what are electrons truly made of? And as this gentle question settles, another begins to surface, guiding you toward the next chapter of this journey. What contradictions appear the moment we try to call the electron a point? Part 2. Why the point electron collapses under its own contradictions. The contradiction appears immediately. A point is supposed to have no size, yet the electron carries spin, mass, magnetic moment, and finite energy, properties that cannot fit inside a volume of zero. This tension has lived quietly in physics for more than a century, a small fracture between equations and reality, waiting patiently to be understood. A point has no room to turn, no space to hold energy, no interior where a magnetic field could settle without spiraling into impossible infinities. And yet, every high-energy experiment, from particle collisions to deep scattering studies, reports the same quiet result. The electron behaves as though its size is smaller than 10 meters, too tiny for any instrument to detect. That paradox has shaped decades of research, leaving physicists with a model that works beautifully on paper, but collapses the moment you try to imagine what it actually means. The tension began in the early 1900s, when classical physics predicted that compressing any electric charge into an extremely small space would demand infinite self-energy. As you draw closer to a point, the electric field intensifies without limit, and the energy stored in that field soars toward infinity, something nature has never allowed to keep the theories from unraveling. Physicists in the 1940s introduced a mathematical workaround called renormalization. It removes the infinities from the equations, leaving behind the correct mass and charge. Richard Feynman joked once that the method felt ridiculous, but also admitted that nothing else worked. Renormalization saves the numbers, but it never explains the thing itself. What prevents an electron from exploding under the weight of its own field? The question deepens when you consider spin. Spin is not literal rotation. You cannot imagine it as a tiny sphere turning in space. It appeared first in 1925, when Samuel Goldschmidt and George Uhlenbeck examined patterns in hydrogen's spectral lines. Their calculations hinted that the electron carries a specific internal angular momentum. But when physicists tried to picture a spinning charged ball that produced the observed magnetic moment, they discovered a contradiction. The surface would need to rotate faster than light, a clear impossibility, so the picture of a spinning sphere was abandoned. The electron was declared a point again. Yet the magnetic moment remains real, so real that penning trap experiments can measure it to more than 10 decimal places. One of the most precise results in all of science. But how does a point create a magnetic moment? The question only grows heavier. Everything sharpened in 1947, when Willis Lamb and Robert Rutherford detected a tiny shift in hydrogen's energy levels, a deviation too subtle for earlier theory to explain. The Lamb shift revealed something profound. The electron interacts with the vacuum itself. Empty space is not empty at all, but alive with fleeting virtual particles. NASA would later describe this simply: the vacuum Sith. If the electron responds to these fluctuations, it becomes difficult to think of it as a perfect, contentless point. Something must be there to interact. Something must carry or store the effect. The puzzle deepened through the 1960s and 1970s at SLAC. Researchers hurled electrons at nuclei with enormous energies, probing smaller and smaller distances. If electrons had internal parts, the scattering pattern would reveal it. But again and again, the electron behaved as if it were point-like, even though the self-energy paradox had not disappeared. In classical physics, the Coulomb field near a point charge becomes infinitely energetic. That contradiction still lurked beneath the numerical successes. The Standard Model chooses to treat the electron as a point excitation of a quantum field, a move that sidesteps the question of shape entirely. But the tension remains. If the electron is truly a point, why do its properties behave as though something intricate is hidden within? The puzzle returns when examining the magnetic moment, the G-factor. Classically, a rotating charge produces a magnetic field, but a point cannot rotate or generate an extended field. And yet the electron's G-factor veers slightly from the simple prediction. A tiny deviation called the anomalous magnetic moment. Experiments match the theoretical value to 1 part in a trillion. ESA researchers summarize this with striking clarity. The electron's magnetic moment reveals its internal dynamics. internal dynamics inside something that is supposed to have no interior. This quiet contradiction echoes through the history of quantum physics. In 1928, Paul Dirac unified quantum mechanics with relativity and wrote the equation that naturally produced the correct spin and magnetic moment. His work predicted antimatter, and Carl Anderson discovered the positron just 4 years later. Dirac's theory stands as one of physics' greatest achievements, but even it describes only how the electron behaves, not what the electron is. The contradiction grows sharper when you consider self-energy again. Imagine approaching a point charge. The closer you move, the more violently the electric field rheses. Classical physics says the total energy diverges. It becomes infinite. Yet the electron has a finite mass. Something must prevent the field from blowing up. Something must regulate the energy at tiny scales. And a geometric point cannot do that. Throughout the mid-20th century, theorists explored extended electron models, spheres, shells, distributed charge, but every attempt collapsed under relativity. No structure stayed stable. The electron returned, reluctantly, to its role as a mathematical point, but the tension never disappeared. As particle accelerators reached higher energies in the late 20th century, experiments probed distances far smaller than before. The electron continued to scatter like a point, even though its measured properties seemed to require more than a structureless dot. In recent decades, astronomy added new layers to the question. Missions studying cosmic rays observed electron-positron pairs forming near pulsars and black holes, appearing in precise quantities predicted by quantum field theory. If electrons can emerge from pure energy, then their structure must be encoded in the fields themselves. A true mathematical point cannot hold such encoded detail. Back on Earth, lasers exceeding 10 watts per square centimeter have begun to reveal nonlinear vacuum effects, faint hints of the physics that leads toward the Schwinger limit. These experiments show that intense fields distort the vacuum, altering an electron's motion. But a point-like object has nothing for the vacuum to push on. Something must be responding. Every observation, magnetic moment, Lamb shift, vacuum polarization, pair creation, scattering results. Self-energy stacks the contradictions higher. The standard model calls the electron point-like for one practical reason. No experiment has yet detected its inner scale. Not because the idea is conceptually sound. This unresolved tension is what led researchers like Williamson and van der Mark to wonder, could the electron hold a structure too small to see, yet real enough to carry every one of its properties? Without contradiction, the toroidal model is one possibility, but it is not the point itself. What matters is the reason such ideas keep returning. The point electron picture simply collapses under its own inconsistencies. And now, at the quiet edge of this discussion, one more question waits patiently for you. If a point cannot hold spin, cannot generate a magnetic field, and cannot avoid infinite self-energy, then what subtle structure must be hidden beneath the surface of the electron? From that stillness, the next chapter begins to form. Part 3. You find yourself returning to a quiet question that refuses to fade. Why does the Compton wavelength act like a soft boundary nature never allows you to cross? Every experiment insists the electron behaves like a point. Yet this single number, its Compton wavelength, marks a limit that no measurement can push beneath. Below that threshold, matter stops behaving like ordinary matter, and light begins to imitate it instead. The story reaches back a century, into a modest laboratory at Washington University in St. Louis, where Arthur Compton directed. High-energy X-rays toured carbon atoms and measured how the scattered light changed. What he discovered reshaped physics. The photons always returned with a slightly longer wavelength, and the size of that shift depended on only one quantity, a constant we now call the Compton wavelength. Compton's result in 1923 revealed a boundary physicists had not expected. Light scattering off electrons behaved as if every electron carried an invisible radius, a tiny forbidden distance of about 2.43 times 10 meters. At that scale, the relationship between momentum and energy changes character. NASA later described, "This transition simply, at high enough energies, light reacts as though something solid stands in its way." But the discovery meant even more. It showed that a photon can only transform into an electron-positron pair once its wavelength shrinks to that same scale. The Compton wavelength wasn't just a scattering parameter, it was the threshold where light gains the ability to become matter. Decades of experiments, larger accelerators, and sharper detectors have never overturned this limit. It remains fixed in the equations, like a quiet marker, defining what radiation can and cannot accomplish. To see why this number matters, return to Compton's table. His tools were simple: an X-ray beam, a graphite target, and a detector that captured the altered photons. Classical wave theory insisted the wavelength should not change at all, but every measurement showed the light returning red-shifted, as if it had surrendered some of its momentum to the electron. This convinced Compton that light must sometimes behave as a particle with momentum, echoing Einstein's earlier idea. And the shift he measured aligned perfectly with the prediction that a photon hands over part of its energy in the collision, the amount depending solely on the angle. The constant governing this exchange quickly took its place as one of nature's fundamental length scales. It defined the wavelength at which a photon carries just enough energy to create matter. Shorter than that, pair creation is possible. Longer, it never occurs. And that leads to a profound truth. Although electrons appear point-like when struck, they refuse to be created unless the incoming photon is compressed to this minimum scale. A true mathematical point would not have such a preferred length. Yet the electron follows this constraint everywhere. Quietly, consistently, universally. The same threshold appears again in quantum mechanics. In 1927, Werner Heisenberg showed that trying to confine a particle to a region smaller than its Compton wavelength forces so much energy into that space that new particles form instead. The uncertainty principle states that the more tightly you attempt to locate matter, the greater the energy you introduce. Once that energy equals the mass of an electron-positron pair, the act of confinement produces new particles, rather than revealing anything smaller. This wasn't philosophical speculation, it became an experimental fact. Collisions at CERN and SLAC confirmed that photons above the Compton threshold generate pairs with increasing likelihood, and below it, they never do. The boundary had become an unavoidable law of nature. ESA's gamma-ray missions support this as well. The Integral Observatory detects electron-positron annihilation lines at 511 keV, exactly the energy predicted by the Compton scale. No deviation appears, not even near black holes, where temperatures soar and space-time bends sharply. NASA's NuSTAR and USAC's M. Newton observe high-energy photons producing pairs at the expected threshold, matching the same quiet rule set a century ago. Wherever matter arises, the boundary stands firm, and so the tension deepens. If the electron were truly a point, why would it obey a length scale at all? Quantum field theory describes it as a point-like excitation with no interior. Yet the Compton wavelength enters naturally as the limit beyond which localization loses meaning. It behaves like an effective size, not a classical radius, but a scale where light and matter trade identities. When physicists say the electron behaves like a point, they mean only that scattering experiments cannot reveal anything smaller. Scattering measures momentum, not existence. And the Compton boundary tells you that probing below that scale injects so much energy that the very particle you are trying to examine dissolves into new ones. It is like trying to inspect a soap bubble by shining light so intense that the bubble breaks before you can see it. In this way, the Compton wavelength forms a gentle safeguard. It prevents you from asking about sub-Compton structure by ensuring that the very act of asking transforms the system. Many physicists describe it as the borderland where photons begin to mimic particles. NASA once phrased it this way: when a photon approaches the Compton scale, it behaves as though a particle is already hidden inside it. A moment from history captures this beautifully. Soon after Compton published his results, Niels Bohr invited him to Copenhagen. Bohr initially doubted the effect. Classical wave theory had served physics well, but Compton arrived with plates showing unmistakable shifts. After studying them for a long while, Bohr leaned back and said softly, "We must accept that nature behaves this way." It was a quiet turning point, a recognition that the electron's properties were deeply quantum, yet tied to a length that could not be reduced. The Compton scale still appears in modern astrophysics. The James Webb Space Telescope detects signals from hot plasmas in early galaxies where electrons interact with intense radiation. These interactions depend on the same threshold energy Compton identified. JWST doesn't measure the wavelength directly, yet its observations reveal electrons behaving exactly as the boundary predicts. Everywhere in laboratory beams, cosmic plasmas, accretion disks, and gamma-ray eruptions, the Compton limit shapes the rules of creation, and here the contradiction sharpens. A point has no size, yet the electron responds as if governed by a scale. A point has no surface, yet photons cannot investigate beneath a certain distance without turning into matter. A point has no internal structure, yet the energy required for pair creation hints at a hidden complexity encoded in the fields themselves. This is why some researchers, including Williamson and Vandermark, explored the idea that the electron might have an effective size, not a classical object, but a scale associated with trapped electromagnetic energy. In their picture, the Compton wavelength becomes the circumference of a looping photon, forming a toroidal path. This could explain why scattering experiments see a point momentum probes cannot tear open the loop, while pair creation requires the full Compton energy to form it. Whether this model proves correct or not, the Compton boundary remains unavoidable. It is built into the fabric of reality, a reminder that the electron is not infinitely compressible, not infinitely localizable, and not entirely compatible with the idea of a mathematical ... And as you approach this quiet limit, another detail begins to emerge. A detail that changes how light might fold into matter and why bending circularly polarized radiation into a closed loop begins to produce qualities like charge, spin, and magnetism. Something remarkable happens when a rotating wave of light is curved into a circle. Along a straight path, circularly polarized light behaves exactly as Maxwell described. The electric field turns smoothly. The magnetic field follows, and the wave travels forward with perfect balance. But once that rotating wave is guided into a loop, its behavior shifts in subtle, extraordinary ways, revealing features that do not exist in free-moving light. Charge, spin, and magnetic dipole moments begin to arise purely from the geometry. To see how this idea even became imaginable, travel back to the early 1920s. At the University of Göttingen, Peter Debye demonstrated one of the first controlled ways to generate circular polarization by tilting birefringent crystals with delicate precision. Meanwhile, at Bell Labs, Carl Taylor, Compton Arthur Compton's brother, used quartz wave plates to rotate polarization for radio experiments. These simple tools allowed scientists to observe rotating electromagnetic fields with consistency and control, opening the door to imagine what might happen if such a field could bend, fold, or close upon itself. You begin with something simple: a wave of light whose electric field spins as it moves, a gentle rotation with no hint of structure inside it. Circular polarization, as NASA describes it, is clean and uniform, a smooth turn of the field with no hidden layers, no preferred orientation, no inner architecture. Nothing about it resembles a particle, but everything changes when that quiet wave begins to bend. Imagine that rotating field as a small arrow turning in time as it glides forward. Now imagine its path curving, folding into a circle. The instant the wave closes into a loop, its rotation and its motion around the curve become inseparable. Two movements, once independent, begin to braid together. From this simple shift in geometry comes the seed of a different idea. An electron, shaped not as a point, but as a torus. A torus is more than a ring. It holds two curvatures at once, one wrapped around its inner opening, the other around its outer circle. When a circularly polarized wave is confined to this surface, its electric and magnetic fields follow both curves at the same time, winding around the structure in a rich, interwoven flow. In the late 1990s, Williamson and van der Mark explored what happens when a photon, carrying exactly the energy of an electron, 0.511 MeV, is folded into such a loop. Using only Maxwell's equations and the measured Compton wavelength, they discovered something remarkable. The emergent structure didn't vaguely hint at the electron. It reproduced its specific traits. One of the most striking is spin. This isn't metaphorical rotation, it is a measurable rule of nature. A full 360-degree rotation doesn't bring the particle back to its original state. It takes 720 degrees. You see this in the classic Stern-Gerlach experiment, where silver atoms split into two spin states rather than spreading into a continuous pattern. The toroidal picture mirrors this effortlessly. A vector carried along the torus while turning around its own axis never realigns after a single pass. Only after two complete loops does it return to its starting orientation. In this soft geometry, spin 1/2 emerges naturally from the blending of two motions, the internal rotation of the fields and the external sweep around the toroidal ring. Then comes the magnetic moment. In a straight wave, the magnetic field curls around the direction of travel. But once the wave bends into a torus, those curls must close upon themselves, forming nested loops locked around the core. This pattern matches the electron's magnetic dipole in both symmetry and direction, not as an approximation, but as a direct outcome of the shape itself. Similar patterns appear in scientific notes on magnetic confinement, where curved electromagnetic fields naturally form stable loops. Next arises electric charge. In classical physics, charge is fundamental, something given, not explained. But on a torus, the rotating electric field develops a global tilt, inward or outward, relative to the surface. Seen from far away, this orientation produces exactly the field pattern of a point charge. An inward lean behaves like negative charge, an outward lean like positive. The positron becomes not a different substance, but the same structure with its motion reversed. This tilt also locks the electron into stability. A torus cannot unwind its topology without destroying the structure. Spin, charge, and magnetic moment become inseparably tied together, which helps explain why the electron shows no hint of decay. Even the size of the structure is not adjustable. Its radius is set by a balance between outward electromagnetic pressure and the vacuum's resistance to extreme curvature. This balance occurs at the Compton wavelength, 2.43 times 10 meters. The same scale appears in pair creation, Compton, scattering, annihilation lines, and high-energy plasmas near black holes observed by missions like NuSTAR, Integral, and JWST. Everywhere matter forms. This radius returns a quiet signature of nature's preference. In this view, a photon with 1 electron's worth of energy naturally folds into a stable loop at that scale. It cannot compress further without creating pairs, and it cannot expand without losing the ordered motion that sustains it. The result is a stable configuration, the electron. Hints of internal motion have appeared before. In the 1930s, Julian Schwinger, studying intense accelerations, noticed patterns implying deeper structure beneath a particle's point-like behavior. His concept of Zitterbewegung, a trembling motion coming from a particle interacting with its own field, suggested unseen internal rhythm. The toroidal idea gives that rhythm a physical form. 2 woven rotations on a closed surface. All of this leads to a gentle but profound realization. Curved circular polarization, shaped with precision, naturally produces the traits of an electron. Spin follows from topology, magnetism from closed field loops, charge from field orientation, size from vacuum stiffness, stability from geometric locking. None of these require extra assumptions. They arise because of the shape, and at the edge of this picture waits the next quiet twist. What happens when the internal motion reverses? When the fields inside the torus flip direction, everything transforms at once. Magnetic moment, electric, tilt, and handedness. The structure becomes the positron. A mirror twin formed not from a new ingredient, but from the same geometry turned inside out. To see why this reversal holds such power, you return to the looped photon. A circularly polarized wave carries rotation like a soft corkscrew moving through space. When folded into a torus, that rotation splits into 2 intertwined motions, the twist around the core and the sweep along the ring. Together they create the spin 1/2 behavior long known in quantum physics. But the torus adds direction. The flow can wind one way or the other. This choice gives rise to the two familiar spin states, up and down, seen since the early Stern-Gerlach experiments. Reversed the flow, and the magnetic field flips. With it, the electric field flips too, turning negative charge into positive. Penning traps have measured this difference with exquisite precision. In the toroidal view, it comes automatically. Change the direction of circulation, and everything reverses except the mass, which remains fixed, because the loop's circumference stays the same. This echoes a moment from 1932, when Carl Anderson saw a particle curve the wrong way in a magnetic field. It had the electron's mass but the opposite charge. It was the positron, the first antimatter particle observed. In the toroidal model, such curvature simply reflects reversed internal orientation. Circular polarization makes this reversal feel natural. Bend the rotating wave into a loop, and its handedness determines the arrangement of fields. Flip the handedness, and the entire configuration transforms smoothly, not violently, but like a quiet turning of a page. This is why some physicists exploring topological field theories describe charge as orientation. The toroidal model follows this idea closely. Matter and antimatter become two stable shapes of the same underlying motion, and beneath everything lies a final calm truth. The torus holds itself together. It needs no outside force. Its own fields support the path they travel, forming a self-sustaining geometry, a quiet, rotating wave wrapped into a closed surface, carrying within it the familiar traits of the electron and the mirrored traits of its twin, all woven from the simple act of bending light into a circle. As long as the loop's circumference matches the Compton wavelength, the fields align constructively and preserve the structure. Reversing the direction does not disturb this alignment. It simply flips the orientation of the fields while leaving the geometry unchanged. This symmetry resembles a familiar principle in modern physics. Operations that reverse orientation often reveal hidden relationships between particles. In the 1950s, studies of parity violation in weak interactions showed that nature distinguishes between left-handed and right-handed configurations. The toroidal structure follows the same idea. The electron and the positron differ not by mass or size, but by an inversion of orientation. A similar pattern appears in the quantum vacuum. When an electromagnetic field approaches the Schwinger limit, around 1.3 times Yp volts per meter, the vacuum produces electron-positron pairs. These always emerge as mirror images: equal mass, opposite charge, opposite magnetic moment, reversed field orientation. NASA describes this with the phrase, "When energy becomes intense enough, the vacuum releases particles in matched pairs." The toroidal model mirrors this naturally. Two orientations of the same trap-like geometry give rise to a particle and its antiparticle. The vacuum is not choosing between different objects, is expressing both orientations of a single underlying structure. But the question of spin states brings the model into sharper focus. Spin 1/2 particles behave in a way that defies classical intuition. They require a 720 rotation, not 360, to return to their initial state. This was one of the earliest clues that electrons do not follow ordinary geometric rules. When the momentum inside the torus loops through two intertwined cycles, one around the ring and one through its center, these cycles overlap in a pattern that repeats only after 2 full rotations. This reproduces the same for symmetry seen. In quantum mechanics, reversing the direction of these cycles yields the second spin state. Nothing else is required. Nature's spin states arise from 2 orientations of the same geometry. The topological picture becomes clearer when examining field lines. In the electron configuration, magnetic field lines wrap around the torus in one direction, reinforcing the internal rotation. In the positron configuration, they wrap the opposite way. Because magnetic moment reflects the sum of internal currents, this reversal produces the observed sign change exactly. The electric field behaves similarly. The geometry forces the field to tilt inward in one configuration and outward in the other, matching the signs of the electrons and positrons charges. Although not part of the mainstream view, this approach aligns with modern studies of topological matter, where field arrangement determines observable properties. The idea that geometry dictates behavior is becoming more common, not less. Astrophysical observations reinforce the symmetry around pulsars. NASA's Fermi Gamma Ray Space Telescope and ESA's Integral detect intense bursts of electron-positron pairs created by powerful magnetic fields. These always appear symmetrically, with opposite magnetic signatures. Near black holes, accretion disks observed by JWST and USDR show emissions consistent with matter-antimatter creation. The symmetry matures the toroidal picture, 2 configurations of the same underlying field topology appearing across extreme cosmic environs, cosmic rays, gamma ray bursts, quasar jets. Matter and antimatter show up in pairs, not as isolated species. This symmetry is precisely what the toroidal model attempts to explain. Though unproven, the model's ability to unify spin states and antimatter under a single geometric reversal gives it unusual explanatory power. The standard model does not attempt to visualize why the spin states exist or why the positron mirrors the electron. It simply lists these as measured properties. In the toroidal framework, the explanation is structural, 2 internal orientations, yielding to spin states and to opposite charges, all while sharing the same mass, shape, and underlying wavelength. Only the direction changes, and as this symmetry settles into place, clean, silent, and unexpectedly natural, another question emerges. If flipping the internal motion creates antimatter, what deeper rule determines the amount of charge that arises from the torus at all? Part 6 begins with this puzzle. Why does a simple energy confinement calculation inside the torus land surprisingly close to the real electron charge? The shock arrives quietly when the trapped photon torus is treated as a region of concentrated electromagnetic energy, and one asks what electric field is required to confine that energy within a loop tied to the Compton wavelength. The resulting charge comes out only about 9% higher than the actual electron charge measured worldwide. No free parameters, no adjustable inputs, just energy density, geometry, and electromagnetic confinement. This numerical closeness unsettles physicists who study the model. In modern quantum theory, charge is fundamental, a value assigned, not derived. Yet this structure suggests that charge may instead arise from how tightly a photon's energy can be folded into space. To understand why the calculation matters, return to the model's central image, a single wavelength of circularly polarized radiation bent into a closed loop, its circumference fixed at the electrons. Compton wavelength about 2.43 times 10 meters. The loop acts as a reservoir of electromagnetic energy. Inside it, the fields reinforce each other, creating pressure pushing outward. To prevent the torus from expanding, an equal inward pull must exist. In electromagnetism, this inward pull is electric field tension, the same tension that surrounds any charged object. Here, the calculation becomes striking. If you take the energy stored in the trapped photon and ask what electric field strength is required to confine that energy within such a small radius, the resulting effective charge is only slightly above the real electron charge. Not exact, but close, astonishingly so, given no parameters were chosen for tuning. NASA's educational notes echo this relation. Electric charge reflects the strength of a field and the energy stored in it. If energy density determines charge, the toroidal model becomes a literal example. Historically, early 20th century physicists tried computing the electron's self-energy using classical electrodynamics. The results diverged. The smaller the assumed radius, the larger the energy, eventually reaching infinity. It was one of the first signs that a point electron creates a physical impossibility. Renormalization patched the math but did not answer the underlying physics. Richard Feynman famously remarked, "We sweep the infinities under the rug." But this offered no insight into why the electron's mass is finite. The toroidal model sidesteps this by treating the electron not as a point, but as a loop containing a finite amount of electromagnetic energy, specifically the energy of a photon, whose wavelength matches the electron's rest mass. The outward pressure is balanced by the inward electric tension. In this view, the electric field is not fundamental. It is required for stability. Charge becomes the price of confining energy within the loop. Using this picture, one calculates the pressure from a 511 Chev photon wrapped around the toroidal path, then computes the electric field necessary to oppose that pressure. The resulting charge is slightly larger than EOF by roughly 9%, but remarkably close for a first-order approximation. Why 9%? Several possibilities exist. The model assumes a perfect, rigid torus, whereas a real electromagnetic structure might deform. Quantum corrections at small distances, similar to the Lamb shift, might modify field strength. Vacuum polarization could reduce the effective field at the boundary, shifting the charge downward into closer agreement. Real electrons interact with the vacuum constantly through virtual processes, which may adjust internal pressure. Whatever the cause, the near match is difficult to dismiss. Williamson and Vandermark expected a wildly inaccurate result, perhaps off by orders of magnitude. When the calculation landed within 10% of reality, they were reportedly stunned. This closeness challenges modern physics conceptually. If charge can be approximated from confined energy, perhaps charge is not intrinsic after all. Perhaps it is a manifestation of energy density within a folded electromagnetic structure. This idea echoes another NASA research note. In certain field configurations, charge separates naturally from geometry. Though referring to macroscopic plasmas, the parallel is striking. The Compton wavelength is key. It is not symbolic, it marks the point where electromagnetic energy becomes matter. A photon with wavelength equal to the Compton scale has exactly the energy needed to create an electron. It is the natural radius for folding energy into a stable toroidal loop. Tighter loops raise energy density, raising required electric tension, raising the charge. Linking the torus to this scale yields a charge surprisingly close to the observed one. Astrophysical data reinforce this relationship. NASA's Fermi telescope observes gamma-ray bursts that produce electron-positron pairs when high energy. Photons meet strong magnetic fields. The threshold matches the Compton scale. ESA's integral sees the 511 keV annihilation line, the exact energy tied to the loop's circumference. Even JWST, though not designed for particle physics, observes hot early universe plasmas governed by this same energy transition. Across laboratory and cosmic environments, the Compton scale marks the boundary between light and matter. If charge reflects the inward pressure required to stabilize the toroidal loop, then charge is not elemental, it is emergent, born from geometry and energy density. The standard model simply catalogues charge. The toroidal model offers a mechanism. As this near match settles into place, another question unfolds. If the electron has real internal size, why does every high-energy experiment show it behaving like a perfect point? Part 7 begins with that puzzle. Every accelerator on Earth reports the same result. When electrons are probed at distances smaller than 10 meters, they scatter exactly like point particles, no radius, no structure. Yet the toroidal model suggests a loop of size tied to the Compton wavelength, far larger than the experimental probes. How can a structured object hide completely? The clue, known since the 1920s yet often overlooked, comes from Louis de Broglie. His idea of internal oscillations explains why particles look point-like at high energy. De Broglie proposed that every particle carries an internal ticking frequency tied to its energy. When the particle moves, relativity shifts this oscillation differently in the forward and sideways directions. One component compresses blue shifted, the other stretches red shifted. Their overlap produces a moving interference pattern, that de Broglie wavelength. This interference wavelength, not the particle's size, governs scattering in collisions. NASA summarizes it simply: a particle's wavelength shortens as it saw. Momentum increases. As electrons accelerate, the beat pattern contracts dramatically. Experiments interact with this pattern, not the internal loop itself. To see how quickly this shrinking occurs, imagine an electron at rest. Its internal oscillation corresponds to its rest energy frequency of 511 keV. When the electron accelerates, the forward-facing portion of the oscillation is blue shifted, compressing its frequency, while the backward-facing portion is reshifted, stretching it. Their interference produces a ripple whose wavelength is inversely proportional to the electron's momentum. Increase the momentum and the interference. Wavelength shrinks at a rate faster than the underlying geometry can shrink. At relativistic speeds, it becomes so tiny that scattering jet sprints cannot resolve anything larger. This is the key. Scattering sees through a length of the interference, not the physical structure creating it. One of the earliest confirmations came in 1927 through the Davidson gem experiment. Electrons striking a nickel crystal produced a fraction, peaks identical totos produced by waves. The peak spacing matched the de Broglie wavelength precisely, proving that electrons display wave patterns under the right conditions. But what happens when electrons are accelerated to near light speeds? Those patterns collapse. At SLAC in the 1970s, researchers fired electrons at nuclei with such enormous momentum that the resulting de Broglie wavelengths were billions of times smaller than the electron's Compton wavelength. The scattering results showed no sign whatsoever of internal structure. No plateaus, no deviations, no ripples. The conclusion many physicists drew was simple. Electrons are points. But that conclusion came from observing the interference pattern, not the internal geometry. A useful analogy comes from acoustics. When two notes of similar pitch overlap, listeners hear a beat, a pulsation that is separate from the actual vibrations of either note. The beat can be much slower than the vibrations themselves and governs what the ear perceives. You cannot deduce the shape of the instrument from the shape of the beat. The beat is only the interaction of the sound waves. Similarly, electron scattering sees only the beat pattern formed by the internal oscillations, not the two-adel structure responsible for generating them. The idea strengthens further when we relativistic time dilation. As the electron approaches the speed of flight, its internal oscillation slows dramatically from the perspective of an external observer. But the forward-moving component of that oscillation becomes compressed extremely high frequency, while the backward-moving component becomes extraordinarily slow. The interference of these unequal frequencies produces a wavelength that shrinks faster than the torus can reveal itself. Even if the toroidal radius were on theater of the Compton wavelength, about 2.43 10⁻12 meters, the de Broglie wavelength at high velocity becomes orders of magnitude smaller. A probe sees only the smaller scale masking anything larger. This relationship has been confirmed repeatedly in high-energy experiments, CERN's LEP. Accelerator collided electrons and positrons at energies exceeding 100 GeV, probing distances smaller than 10 to the power of -19 meters. ISA's gamma-ray observatories detect electrons moving at relativistic speeds near neutron stars, showing identical scattering behavior. Even NASA's measurements of cosmic ray electrons traveling through the interstellar medium reveal that their interactions follow Broglie's wavelength rule precisely. Every one of these observations reinforces the same message. The wavelength collapses faster than the structure. As a result, no experiment can reveal the two-adel interior. Not because it isn't there, but because its method of probing shrinks the interference scale to the point where the structure cannot imprint on the measurement. A historical moment helps bring this into focus. In the 1950s, physicist Murray Gell-Mann wondered aloud why point-like scattering should be taken as literal evidence of point-like structure. He argued that the objects we probe at high energy may have complex internal motions that create wavelengths far smaller than the structures themselves, and therefore scattering results reveal only the interference signature, not the. Decades later, when quark scattering data revealed point-like behavior inside the proton, Gell-Mann's argument resurfaced. Quarks appeared point-like because the wavelengths used to probe them shrank faster than any internal size the proton could reveal. This is the same mechanism that could hide an electron's internal toroidal structure. The two-adel model supplies one additional layer of explanation: the energy circulating inside. The loop produces a natural internal frequency, the circulation rate tied to the Compton scale. When the electron moves, this internal circulation combines with external motion to create two competing oscillations L. Their interference generates the de Broglie wave. That wave becomes the shadow by which experiments observe the electron. The loop remains behind the shadow, never directly touched by the probing energy. Another supporting linear evidence comes from astrophysical plasmas. JWST has observed early galaxies filled with hot, ionized gas where electrons move at enormous speeds. These electrons interact with photons in ways that match DEG's predictions exactly. In high-temperature regions of galaxy clusters, measured by ISS-XMM Newton, electrons scatter in a manner identical to their behavior in particle accelerators, confirming that scattering is governed by interference wavelengths, not internal structure-crystal environments separated by billions of light-years. The same rule holds. Scattering resolves the BIT pattern of internal oscillations. The geometry never enters the observable domain. This is why the electron can have an internal size in the 2D picture and still behave as a perfect point in every high-energy experiment. The probe does not see the torus. That probe sees the rapidly shrinking wave that rides on top of it. The deeper implication is subtle but powerful. Point-like behavior does not imply point-like existence. It only reflects the scale at which the interference pattern can be disturbed. Once this becomes clear, the electron's dual character, structured yet point-like, no longer appears contradictory. It becomes a natural consequence of how motion transforms internal oscillations and how experiments sampled these than the underlying geometry. And as this quiet resolution settles in place, another question waits ahead. One drawn from the behavior of their vacuum itself, which seems to bend, shift, and even create particles when electromagnetic fields become intense enough to reshape the fabric of empty space. What role does the vacuum play in shaping the electron structure? And could it be the hidden scaffold that folds light into matter? Part 8. Why might the vacuum itself be the hidden architect that bends light into a particle? There is a moment in high-energy physics that feels almost impossible the first time it's encountered when an electric field grows strong enough. Empty. Space stops behaving like emptiness and begins to tear electron-sand postrons out of nothing. But raw energy, this threshold known as the Schwinger critical field, sits near 1.3 * 10 to the power of 18 volt per meter, and it quietly reveals that the vacuum is not a blank backdrop at all. It is an active medium with structure, stiffness, and the capacity to erupt into particles when pushed hard now. That single fact places a new light on Thuidal electron model. If the vacuum can create electrons from radiation, might it also be the hidden scaffold that folds a photon into a stable torus at 0.511 MV? The answer begins with the surprising behavior of the vacuum itself. When physicists speak of the vacuum in quantum field theory, they do not mean an absence of everything. They mean the lowest possible energy state of space, a seething, fluctuating sea where virtual particles appear and dissipate quickly to be directly observed. NASA describes this simply. The vacuum is not truly empty. It constantly seethes with pairs of virtual particles under normal conditions. These virtual pairs have no lasting effect on matter, but when an electric field surpasses the Schwinger limit, the vacuum cannot contain them anymore. The pairs are pulled apart and become real electrons and positrons. It is in this threshold behavior, this non-linear violent response that the 2D electron model finds one of its most compelling clues. Because if the vacuum can create pairsat, the moment energy density becomes intense enough, then a photon trapped in a tight loop might generate the same local conditions. To see how this connects, we return to Julian Schwinger's groundbreaking calcul. In 1951, he showed that when vacuum polarization is pushed beyond a certain field strength, the probability of pair creation increases dramatically, effectively allowing energy to manifest as particles. That field strength corresponds almost exactly to the electric field surrounding an electron at distances much smaller than its Compton scale. The electron's own field reaches values that approach the critical magnitude, a fact that has intrigued theorists for decades. If the electron were truly a point with an infinite electric field at zero distance, the vacuum would tear itself apart constantly. That does not happen. Instead, the electron's field saturates in a way that prevents divergence, suggesting that something about the vacuum, or the electron itself, regulates its field before it reaches destructive intensities. This is one reason some physicists consider the possibility that electrons may have structure that prevents infinite fields from forming. In the 2D model, the trapped photon's energy density is the source of the electric field. As the electromagnetic loop curves around itself, its field presses outward. The vacuum pushes back. The balance between these forces determines the radius of loop, and that radius matches the Compton wavelength. This is striking because the Compton wavelength appears naturally in both pair creation and the 2D confined scale. It is as if the vacuum enforces a minimum foldable radius. Any attempt to confine energy below that limit triggers pair creation, while confinement at that scale become comestible. This echoes a line from an ESA commentary on strong field environments. The vacuum behaves like a material that resists extreme fields, a resisting vacuum. A vacuum with stiffness, exactly the kind of environment where light could fold into a stable, self-sustaining structure. The torus would not float in emptiness. It would be supported by the vacuum's nonlinear response. To understand how the vacuum could support such a structure, we explore phenomena observed in neutron stars, magnetars with magnetic fields exceeding 10 to the power of 10 Tesla. Push the vacuum into regimes where polarization effects become enormous. NASA's NISA and ICES XMM Newton missions have recorded spectra from these stars that bear signatures of vacuum by referring a state in which empty space behaves like a polarizing crystal. This is not speculation. This is a measured property of the universe. If a vacuum can act like a polarizing medium under extreme fields, it is reasonable to suspect that it may also influence electromagnetic waves confined at scales near the Compton wavelength. This brings us to the heart of the 2D model, a photon with energy 0.511 MeV. Exactly. The energy required to create an electron has a frequency so high that its fields oscillate over a timescale, incredibly sensitive to vacuum polarization. As the photon bends into a loop, the vacuum's response modifies the field lines enough to stabilize the curvature. Without the nonlinear properties of the vacuum, the wave would simply radiate away. With them, the wave finds a radius where outward pressure and vacuum resistance match. This match occurs at the Compton scale, the same scale observed in pair creation. This connection suggests a powerful possibility. The vacuum sets the electron's size not through arbitrary parameters, but through its inherent inability to remain passive under high-frequency electromagnetic stress. Where the vacuum stiffens, the photon bends. Where the photon's field aligns with the vacuum's distances, the torus stabilizes. The electric field pulls inward. The trapped wave pushes outward. The balance becomes the particle. The vacuum does not merely respond to the particle. It participates in its creation. Evidence for this kind of nonlinear vacuum behavior extends far beyond theoretical predictions. Experiments using ultra-intense LOCIA-SAC, as those at the extreme light infrastructure facilities in Europe, have observed early signs of vacuum nonlinearities at field strengths, order Ceph magnitude, below the full Swinger limit. These include changes in refractive index and photon-photon scattering effects once thought impossible. Photon-photon scattering is a special eROSITA. It shows that photons can interact indirectly through the vacuumers. Virtual electron-positron pairs briefly emerge and mediates interaction. This means that the vacuum itself can redirect electromagnetic energy, shaping its path and altering its curvature. If this is correct, then the vacuum is not just a background. It is a sculptor. It shapes electromagnetic fields, resists their extremes, and determines the scale at which energy can compress into matter. It does not allow infinite charge densities. It does not allow unconstrained field strengths. It forces structure. This leads to a remarkable perspective. A photon may not become an electron bees. The photon chooses to fold. But because the vacuum refuses to let high-frequency energy remain unconfined, the vacuum channels it into a geometry compatible with stability. The torus, this quiet enforcement echoes a line from NASA's overview on peer creation. When energy density becomes extreme, space cannot remain empty. At the threshold of 0.511 MeV, the vacuum transitions from passive space to active architecture. It shapes light into matter. It stabilizes the two-idle loop. It defines the radius. It sets the charge. It establishes the mass. Every property of the electron may be tied to how the vacuum behaves under extreme electromagnetic stress. The electron becomes not a point, not an arbitrary field excitation, but a stable curvature in a medium with measurable linear properties. Astrophysical evidence strengthens this idea further. In regions near black holes where energies climb toward mesoscales, JWST and NuSTAR have observed plasma structures where photons and electrons continuously interchange identities. These environments display rapid percreation and annihilation cycles, governed by vacuum response. The vacuum behaves consistently across the cosmos, from laboratories to neutron stars to centers of galaxies. Its resistance to extreme fields is universal. Its role in shaping electrons cannot be ignored. This perspective transforms the question, what is the electron made of, into something deeper. What is the vacuum capable of when electromagnetic stress reaches its natural limit? And as this idea settles, that the vacuum may be the hidden architect guiding energy into thetoidal shape that forms the electron, another detail waits ahead, delicate and sharp. How can a structure shaped by the vacuum remain perfectly stable over cosmic timescales, while heavier particles decay and vanish? Part 9. Why does charge conservation lock the electron into immortality when heavier particles decay? Every particle we know seems to have a built-in clock except the electron. Neutrons drift for only about 15 minutes before falling apart. Muons survive just 2/millionths of a second before vanishing. Even exotic short-lived particles observed at CERN endure for less time than a camera shutter. But the electron does not fade, change, shrink, loosen, or unravel. It simply persists unchanged across billions of years, from the formation of the first atoms to every moment unfolding now. This durability is notably remarkable. It is unmatched, and the 2D model offers a quiet but powerful explanation. The electron stability is not a miracle of nature, but a consequence of topology tied to a rule so strict that no experiment has ever found a way around it. Charge conservation. To understand this connection, we begin with the behavior of unstable particles. The neutron, although it feels solid inside atomic nuclei, is unstable in isolation. Its decay produces a proton, an electron, and an antineutrino. All three products obey charge conservation. The neutron starts with no net charge, and the decay ends with a positively charged proton and a negatively charged electron that sum to zero. Muons behave similarly. These heavier cations of the electron carry the same negative charge, but their internal structure, whatever it is, cannot sustain itself long. Within microsecons, the muon turns into an electron and two neutrinos, once again distributing energy without altering total charge across every setting where charged particles appear in accelerators. In cosmic rays, in radioactive decay, one principle never falters: charge never vanishes. NASA states it simply: electric charge is conserved in every process we know. This rule is older than quantum theory itself, and somehow it still governs every experiment we perform. You begin to wonder what this has to do with the electron's unchanging presence. The toroidal model offers a quiet hint. In this view, the electron is not a mathematical point, but a loop of confined electromagnetic energy. Its charge is not an inherited property. It is the orientation of the fields wrapped around the torus, a twist built into the geometry itself, like a knot. In a rope that remains unless the rope is cut, the charge is written into the topology. If that picture is true, the electron stability is no longer mysterious. Topology does not easily unravel. Charge cannot fade away because the structure that carries it cannot unwind. Without breaking a deeper rule woven into the vacuum, other particles do not share this constraint. Neutrons and muons lack this inherent topological protection. They decay when conservation laws allow their components to rearrange. The muon, for instance, contains internal interactions that make it energetically unstable. It can shift into lighter particles as long as total charge stays the same. But the electron has nowhere to go. It is already the lightest charged particle that exists. No lighter configuration can hold its charge. Nature cannot move that charge anywhere else. And so the electron remains locked into permanence. A moment from the past captures this. In 1957, deep underground detectors searched for traces of electron decay, faint flashes signaling a transformation into lighter particles, but nothing appeared. Years turned into decades, and new detectors were built, first in Japan, then larger ones, than Borexino in Italy. Billions upon billions of electrons flowed through them. Not a single decay event was ever seen. Today, the electron's lifetime is known to exceed 10 years, 100 trillion times the age of the universe. No other particle approaches such stability. The standard model accepts this as fact. The toroidal model tries to explain it. In that picture, the electron endures because its geometry cannot unwind without erasing its charge. Charge is not a separate ingredient. It is a directional pattern held in place by the toroidal fields. To remove it, the entire twist would have to undo itself. But the fields shaping the torus are locked into that twist. They cannot collapse without violating. Charge conservation. The electron's endurance becomes a geometric requirement. Not mysterious, not arbitrary, simply structural. Some speculative models extend similar loops to particles like the muon, but their higher mass means their internal energy pushes outward more strongly. The vacuum lets those structures relax, allowing them to fall into lighter combinations while preserving charge. The electron cannot do that. It sits at the lowest possible mass for a charged particle. Any attempt to relax would require losing charge, and losing charge is forbidden. Astrophysical observations echoed this same rule. NASA's Fermi telescope detects high-energy electrons born when cosmic rays strike interstellar gas. These electrons drift for millions of years, spiraling through magnetic fields, scattering off photons, and interacting with shock waves. They shed energy, wander, radiate, but they do not decay. Near pulsars, where electrons are accelerated almost to the speed of light, they showed the same endurance. Observations from the Integral mission watch electron-positron pairs appear and vanish, yet the electrons that survive remain unchanged. Even in the violent environments near black hole accretion disks, glimpsed by JWST electrons remain electrons. Intense heat, extreme fields, and turbulent plasmas do nothing to loosen their structure. All of this suggests that electron stability is not merely a feature. It is a limit set by geometry and conservation. In the toroidal view, charge conservation behaves like a knot in the field. The knot cannot slip free without tearing the field lines themselves, and field lines cannot tear unless charge is destroyed. But charge cannot be destroyed, so the knot endures. NASA's plasma physics notes phrase it gently. Field topology determines stability. Applied to the electron, the statement becomes literal. The toroidal topology ensures stability because untying it would violate charge conservation. This gives the electron a kind of topological permanence that heavier charged particles lack. The muon carries charge, yet its geometry cannot hold. It collapses into an electron, sending its extra energy into neutrinos. The electron has no such path. It already occupies the simplest configuration compatible with its charge. One last detail sharpens the picture. When electrons meet positrons and annihilate, the toroidal patterns do not slowly unwind. They collapse instantly, releasing their stored energy as gamma rays at 0.511 MeV. The symmetry between their creation and disappearance hints that the toroidal loop is not only stable but deeply consistent with how pairs form in the universe. Across cosmic rays, magnetar flares, and collider beams, the electron's shape, however tiny, survives untouched. Only its opposite, the positron, can erase it. Nothing else can. This leads to one final, quiet thought. The electron's longevity is not due to simplicity. It endures because its design is complete. As that realization settles, a new question begins to take form. A soft inquiry shaped by symmetry, structure, and the energy that has guided your path. If charge, spin, and stability arise from geometry, what deeper pattern might bind all particles, electrons included, into one unified fabric where matter becomes nothing more than structured disturbances of the vacuum? in every corner of the universe. No matter how particles are created, one truth remains unchanged. They arise from the structure of the vacuum itself. Once formed, their traits never drift. The charge is always the same, plus or minus 1.602 times 10 coulombs. Their spin remains 1/2. Their mass holds steady at 0.511 MeV/s squared. Across galaxies, star-forming clouds, and laboratory beams on Earth, these values never shift. Such uniformity hints that these qualities are not chosen by chance. They are sculpted by the geometry of the vacuum. JWST's deep views of early galaxies reinforce this quiet idea. The electrons that shaped the first atoms behave exactly like the electrons you work with today. Even though they formed under temperatures and pressures nothing like those of the present universe. This sameness strengthens a simple hypothesis. The vacuum sets the rules, not history, not environment. The vacuum is identical everywhere, and so the electrons it shapes follow the same blueprint everywhere. From this emerges a deeper, more daring question. If the vacuum fashions electrons, why not protons, neutrons, mesons, even quarks? Quantum field theory already tells you that every particle is an excitation of an underlying field. But the toroidal model adds a geometric layer. These excitations may not be simple ripples. They might be enduring patterns in the curvature of the vacuum, anchored by the same stiffness that grants the electron its incredible stability. Heavier particles decay because their internal patterns are unstable. Their geometries press too tightly, hold too much energy, or clash with the vacuous resistance. When they release that excess energy, the vacuum relaxes them into simpler shapes, most often electrons, photons, or neutrinos. The electron endures because it represents the simplest stable twist that can hold electric charge. The photon endures because it is the simplest pattern with no charge at all. Neutrinos persist because they are nearly weightless and electrically neutral. Seen through this lens, the particle zoo becomes far less chaotic. Everything becomes a family of possible twists, folds, and vibrations of the vacuum. Matter becomes structure. The vacuum becomes the medium beneath everything. Carl Sagan once wrote that we are a way for the universe to know itself. Under this interpretation, the words take on a new literalness. If matter emerges from strained patterns in the vacuum, then the universe shapes itself into forms capable of observation. This idea also aligns with another quiet truth: the vacuum contains enormous energy. NASA describes it this way: vacuum energy is everywhere, shaping particles even in complete darkness. If the vacuum holds energy, and if it can sustain patterns, then particles may simply be the allowed shapes, the stable ways fields can fold without collapsing. Here, the toroidal electron model becomes a hint rather than a full answer. It shows that a trapped photon can naturally acquire mass, charge, and spin without being a mathematical point, and without relying on arbitrary constants. It suggests that the vacuum can support structures that behave like matter, and that this ability might extend to all particles. Clues from across physics point in the same gentle direction. Pair creation reveals that the vacuum can turn energy into matter. Vacuum birefringence shows that empty space behaves like a physical medium. Cosmic electrons demonstrate that particle properties remain unchanged across billions of years. Scattering Experiments hint that hidden structure can exist beneath wave-like behavior. Topology shows the stability can emerge from geometry alone, woven together. These threads whisper an unsettling yet elegant possibility. The universe may not be composed of tiny building blocks at all. It may instead be made of stable distortions. In the vacuum patterns held in shape by the quiet strength of empty space. And as this thought settles softly into your mind, another reflection riseth with it. Not sudden, not loud, simply present at the edge of this long journey you have taken. If matter is structure in the vacuum, then everything you see and touch may be gentle patterns held together by an invisible, ever-present fabric. Thank you for sharing this quiet exploration. If this story offered you even a moment of calm or clarity, a small like or a simple tap on subscribe is a warm encouragement that helps me continue creating these night journeys. And if you feel comfortable, I would truly love to know where you are listening from, and any thoughts or suggestions you wish to share. Your words help guide the path forward. Wishing you a restful night, slow breathing, and a peaceful drift beneath the soft, patient hum of the universe.